In this lecture I want to introduce the topic of function overloading. Now this lesson is already one of the longest lessons, if not the longest lesson in the course so far. That is of course on the topic of pointers and references primarily. So my initial plan was to introduce function overloading in some of the upcoming lessons on object-oriented programming and so on, but we already have a lot to cover in those lessons anyway. So on object-oriented programming we have inheritance, friend functions, constructors, destructors and all of that stuff. And also in some of the upcoming lectures I want to discuss L values and R values and various other things that have to do with references and some of the benefits that you get with some of those types of references that you can do. And some of that comes into play when you overload functions. And for that reason I'm introducing function overloading right now so that we have it down and it's out of the way. Now basically what function overloading allows is for multiple function declarations that have the same function name. Now a few important notes on this. Each function overload must have a different signature, otherwise you'll have some conflict or some error. Now what is a signature? We've talked about the prototype or the declaration previously, but the signature is slightly different. The signature includes the function name and the formal parameter list. Now of course when we overload the goal is to use the same function name, right? So since we use the same function name, the formal parameters must differ. That is the number, order and types of the parameters. Also important to note is that the return value is not considered as part of the signature. Firstly, an example of what not to do. So I have these two prototypes or declarations that have of course the same function name, so get average score. This will not compile. So even though the prototypes are different because the return types are different and the return types are part of the prototype or the declaration, but the return type does not form part of the signature. And the signature is again the function name and whatever we have with the parameters. And as you can see here, we have 3 integers in both of these declarations. Another important thing that you need to note here is even if you go and change the parameter names, so let's say in the second declaration you change this from XYZ to PRQ for example, that's not going to make a difference. You'll still get an error. And if you remember from the first module where we discussed functions and function prototypes, you don't really even need the name for the parameter in the prototype. It is important in the definition of the function, but not so much in the declaration or the prototype. What is important is to declare the type for each parameter. So this next example will actually compile fine. In the first declaration, the signature is get average score, and then I have 3 parameters, all 3 of which are integers. In the second declaration, the signature is get average score, and then I have 3 parameters, all 3 of which are of type float. So again, the name of the parameter is not that important, so XYZ, P, Q, R, that is not important. Instead of using P, Q, and R, I could have used X, Y, and Z in the second declaration as well. For the second signature, it really doesn't matter, but the point is the types of the parameters do differ. Now let's say they were the same, all of them were integers, but in the first one I had 2 parameters and in the second one I had 3 parameters. That would be fine as well, so the amount of parameters do matter, and then also the order, so I might have a float for the second parameter in the second declaration instead of having them all be integers, and those will then also be considered 2 different signatures. Once again, what the function returns does not form part of the signature, and this is great because it means that we are not sort of forced to use the same return for each different declaration or definition, right? Because in the first one I might want to return a float, and in the second declaration maybe that one takes in doubles, and then maybe I want to return a double so that I don't have to convert and so on. Okay, so with this out of the way, let's go and look at a few examples in Visual Studio. In this example I have a simple function called print. It takes in a single argument. I'll just duplicate that to create an overload, and let's say I change the name. If you think for a second what the signature is, alright, we have a signature right here and a signature right here. It includes the name and the parameters. Both of these overloads have the same parameters because it is a single parameter and both of them are of type int. So this means if I build and run this, we'll actually get an error. Function void print int already has a body. You'll notice print int, so it doesn't show the names of the formal parameters. Okay, so just because you change the name, that doesn't really matter. You have to change the type. If this was a different type, then that will work fine. I'll actually change that to float. You can use the same or a different parameter name, it doesn't really matter. And then this print function is now successfully overloaded because the signature is different. This will mainly boil down to the formal parameter list. So we want to change again the type or the amount of parameters or the order of your parameters. Okay, I can build and run that and this will work fine now. And let's say I change this here to something like 55.5. If I build and run that, we'll get some sort of ambiguous error. So ambiguous call to overloaded function, trying to match the argument list double. So if you remember from the first module, once again, this here is considered a double. So if I change this here to a double instead, then this will work fine. Change that back to a float, and then over here, of course, we can specify a literal to be a float or to be recognized by the compiler as a float by postfixing the literal with the F character, and then this will work fine. Also, if I hover over this function now, we get this helper with more information. So it gives us the prototype of the function, so what it returns, the parameter list, and so on. Then you'll see something new, so we have +1 overload. This helps us identify functions that are overloaded. Also, if I left click in here once, I can press Ctrl, Shift and Spacebar, and that will bring up this IntelliSense once more, and we now get the overloads. You can press the up and down arrows to go through the overloads. So this is the one that we are currently using. If I go down one, we have int x. So that's right here. Click in here and then Ctrl Shift Spacebar to get that. Also, as you'll see later on in the module, you can sort of separate your code files. So you can have a header file and a source file, as I showed you briefly in some of the previous lectures and in module 101. And then these helpers will become really important, because otherwise you'd have to go to a completely different code file, whether that's a source file or a header file, just to see how to use the function. So again, these helpers are very useful. Of course, you can have more than one overload, so you can have maybe another one for a character, another one for a string. You can have another one with a double, for example. So we have 3 overloads here. And the compiler is going to deduce which one to use based on the arguments that we feed the function. Previously we saw that if I have a float, so if I remove this overload here and we have this function with the float parameter and I pass in a double, we'll get an error. So we have an ambiguous call to overloaded function error. I'll just set that back to a float. But if we change this to a double, so that parameter is now a double, then it's fine to pass an argument of type float, because that float will essentially get promoted, as it is referred to a double. So you will not lose data when you go from a float to a double. It's only when you go from a double to a float that you have the potential to lose data, right? So this will work fine. You'll see this compiles fine and everything. And so now we can use a float or we can use a double. And both of those will work fine with a single overload. Again, that's why I spent a lot of time in the first module talking about the different types and type sizes as well, because that's kind of glossed over in most courses. But it's quite fundamental in C++ to have an understanding of the different types and those type sizes. Of course, with smaller values like 55, you won't have much of a problem, but with huge values you can run into issues. Another interesting thing that comes into play with function overloading is default arguments. Let's say we take out the argument in this print function call. If we try and build and run this now, the function does not know which one to use. No overloaded function takes 0 arguments. So we can add a default argument to one of these. Let's say the print function that has an integer parameter. I do a default argument, so I set x equal to 5. Build and run that, and that works fine. And the same one with the double. So if I do a default argument here in the print function with the double, it should print that one out. In other words, the compiler will deduce which function to invoke. And because this function here has a default argument and we don't specify an argument in the function call, then it will go and use the one with the default argument. But of course, if we now have two function overloads with default arguments and we don't specify an argument in the function call, then once again we'll get an error. Some ambiguous call error. Now I can just do 5. So it will invoke the print function with the integer parameter. And of course it will use our argument. Or the function with a double argument, so it all depends on the argument that we pass in to the function and when we call it. Alright, in this quick example I have a multiply function, and previously I mentioned the return type is not considered as part of the signature, so when we overload a function, that is not taken into consideration. And you can already see the red squigglies will get an error, because in both functions we have as parameters we have integers. So if I try and use that, of course we'll get a bunch of errors, redefinition and so on. And the help is pretty useful in some cases. It says here, cannot overload functions distinguished by return type alone. So instead, I'll do something like this, like a double for example, and this should work fine now. Might want to declare this as a double actually for this demonstration. Another thing that I'd like to mention again is I can actually remove the integer version because, so these parameters accept doubles, right? But it's fine to pass in integers. Those integers will once again get promoted to doubles. So I'll just build and run that, and that'll work. So just another quick example on that. Abstraction is another major focus of this module, so module 102. And we also have procedural abstraction. Now firstly, what do I mean by procedural? Well, this relates to functions or procedures. Instead of calling it functional abstraction, we refer to this as procedural abstraction. In computer science, the term procedure is more common. So what is this idea of procedural abstraction? Well, it's the design or usage of black box functions, basically. And so what's a black box? Well, basically what it boils down to is you may know how to use some device or thing, in this case a function, but the implementation, or in other words how it works under the hood, is hidden, right? So this idea of abstraction, this allows us to focus on what we want to do instead of how. The how is already taken care of, basically. So the function definition in that case already exists. Some programmer already went ahead and implemented that function. Let's say we use some function from the standard library such as ABS that we've already discussed and so on. We can just use it. We don't care about how it is defined or how it works under the hood, basically. We just want to use it, and in that way we also don't have to reinvent the wheel each time. We can just use existing functionality. And that's why a lot of programmers love the Qt or Qt IDE and programming environment, because a lot of classes and functionality already exists for us to go and write cross-platform and great looking applications and user interfaces. Now, a well-designed function can be used like a black box. All the programmer needs to provide are valid arguments, and the black box function will then provide the results. The programmer should not need to look at or understand the function definition in order to use it. Right, so I have some function, such as the ABS function that we talked about previously. Maybe the helper comes up and it will show you the prototype or the declaration. And in that way, all you need to know is what arguments that it expects. So you pass in the arguments, and then that function will return something or, do what you want it to do basically, without you having to understand exactly how it performs those tasks. And that will wrap up this lecture on function overloading.